And we are delighted to have Professor Fedor Sukochev as our distinguished speaker. Professor Sukochev, an academician of Australia, is a world-renowned mathematician recognized for pioneering analytical approaches to complicated interdisciplinary problems. He is a leading expert in non-commutative analysis, non-commutative geometry, and non-commutative probability. Let's welcome.
Thank you very much for this invitation and the possibility to visit Beijing. I'm very grateful to Professor Jinsong Wu for this invitation. Originally, I might say that this was having some ulterior motives by coming here, because I wanted also to support my younger collaborator, Fulin Yang, who is now will becoming member of this institute. And in fact, I was planning to employ him at University of New South Wales, but there was this administrative difficulties which I could not overcome, and so I'm very pleased that here he's got the good place to live and work, and that I could continue my discussions of mathematics with him. And I also must say that this work which I was talking about, this is joint work with Fulin, also with Dmitry Zanin and Dojin Zhu. And in fact, Fulin helped me to prepare this talk. And when anything will be not clear in my talk, we will ask Fulin, not me. That's what we will do. He's here. He's here. He's here. Right. So the title of the talk is Optimal Distribution Estimates for Commutators and Marcinkiewicz Multipliers. And my guess that maybe very, very few people in the audience heard those words before, at least know about this theme, about anything. So it's a technical thing, but mathematics is a technical science anyway. I will be trying to, you know, avoid as much as I could the technicalities, but deliver some ideas what is behind our work. This work was initiated very, very long time ago, so I personally coming to this topic and to this ideology for very, very long time. And I will try to explain what actually this main idea, what we are really doing here. So I'll start with a discussion of the classical Cesaro operator. So that's coming from Cesaro operators certainly were coming much earlier than Harding Littlewood in 1930s, but frequently becoming mathematics. A lot of the results about this Cesaro operators are affiliated with these two names. And the main results that this Cesaro operator sending LP to LP whenever P is strictly between greater than 1. And well, okay, we are in the Banach spaces setting, so we can talk about a dual operator, a joint operator, C star. And then C star works, acts boundedly in all LPs when P is greater or equal than 1, less than infinity. These are, as I said, a very beginning of functional analysis as we know it now. Even, as I said, Cesaro operators certainly were studied much before 1930s. And this is, in fact, those results are very indicative how usually people approach to the study to those operators. We are looking at a single space, let's say LP. So the LP are the most, say, well-known spaces in mathematical analysis. And we are looking, well, okay, so we have this or that operator which acts on this or that Banach space, and we are looking, first of all, how it behaves in LP. And then, well, okay, this is the fundamental results about those Cesaro operators. So let's keep this in mind. Yeah? It is the Banach space consisting of the sum of two functions. One function from L1 and another from L infinity. It's also a Banach space. We can normalize it, and so this is written in such a way simply to avoid discussions where C and C star acting. So they're acting on these sums of those spaces. Next is the so-called Hardy-Littlewood maximal operator. So how is this maximal function is defined? That's the definition. So we're looking at the supremum of all of the expressions like that. So Q is some cube in Rd. If d equals to 1, then it is just an interval. And then, okay, so you take the point x belonging to this interval, you integrate the function, then you normalize this integral, and you look at the supremum of all of those things. This idea of this thing is again also coming, this operator, maximal function, maximal operator, is actually coming from the also from the very beginning of functional analysis. It's coming from the Lebesgue integration theory. With the help of those maximal functions, you can obtain Lebesgue differentiation theorem. And here some motherhood statements that maximal functions has wide applications in harmonic analysis, partial differential equations, and so on, so forth. Again, just as I said, just simply let us keep in mind that this is very important operator in analysis, and there are plenty of the results which describe the behavior of this maximal function, maximal operator. Okay, so the first display on this slide introduces the notation mu. And this, I will have to stop a little bit to discuss this notation mu. What is this notation? So you see some formula. You look at this formula. If you didn't see it before, you understand nothing. So nothing can actually. But I will explain this in a very simple way. With every, say, let it be either real or let's be positive function or real value function. With each of these functions, you can always associate the distribution function. So it is the measure of those points where my function is greater than lambda. So df of lambda is the measure where f of t, measure of all points t, where f of t is greater than lambda. So everybody here certainly know what is the distribution function. So you can look at every function you associate with this distribution function. And then what is mu? Roughly speaking, mu is simply the inverse of distribution function. So if the distribution function, say, monotonically decreasing, then it is precisely the inverse. So for the duration of all this talk, you can simply think that what is written mu here, it is simply the inverse of distribution function. Generally, you simply can think that I'm talking about the distribution functions and nothing else. Well, have a look at this also very old results. There are a few names here. So you see, this is again coming to the very beginning of functional analysis. And then it happens that people who were studying these maximal functions, as I said, it was very important functions coming from the Lebesgue differentiation theorem yet. And then you will see that, in fact, distribution function of maximal functions is equivalent to the distribution function of Cesaro operator applied to the same function f. That's the beginning of all ideology which I'm trying to convey today in this talk, that we can speak, we should not really here thinking about the, say, LP spaces. There is nothing here what is about LP spaces. But here this statement is already allows you to immediately obtain the corollary that, for example, the maximal functions is bounded whenever Cesaro operator is bounded. On the previous slide, we saw Cesaro operator is bounded on all LP spaces. So from here, we can see that immediately that maximal function is also bounded whenever Cesaro operator is bounded. So this simple import of what I'm trying to say, that we can forget actually about those single spaces, LP spaces. What we really need to concentrate from the very beginning in these studies is about the distribution functions or rearrangements, inverses of this mu is called rearrangements. These are inverses of distribution functions, nothing else. And it is a deeper study because when you already know everything about the distribution, then corollaries for LPs or anything like this is trivialities, immediate corollaries. So that's the one of those things which I would like you to keep in mind. The next point of motivation is coming from the classical theory of Calderon-Zygmunt singular integrals. So, okay, so we're looking at this. So, you know, this is our usual integral operator with a kernel K, say on RD, and then this, you know, this is the, again, it looks very technical for those who did not see this before, but for those who saw it, this is the standard assumption which allows to Calderon and to Zygmunt to develop this theory of Calderon-Zygmunt integral operators. So we're always thinking that K satisfies this set of technical conditions. So what did the people do with this one? Well, Calderon-Zygmunt, 1952, famous paper, Acta Mathematica, they proved the following result that such any standard Calderon-Zygmunt integral operator sends L1 into the weak L1 and LP into the LP whenever P is strictly between 1 and infinity. Of course, all of those things are motivated by this fundamental example of Calderon-Zygmunt by Hilbert transform. Hilbert transform is here. Hilbert transform also was studied beginning at least from 1909, and this result of this first part of the Calderon-Zygmunt, this is, of course, analogy. Not simple analogy, but still analogy of the fundamental result by Andrei Nikolaevich Kolmogorov, 1923, that Hilbert transform sends L1 into the weak L1. Kolmogorov did it in slightly different terms, but meaning is exactly the same. Of course, there was also very famous things which called Riesz transforms on RD. Plenty of the papers on the behavior of the Riesz transform, and also whenever they are bounded, and these are also now say boundedness of the Riesz transform, and this estimate called weak type 1 estimate. This is also covered by this Calderon-Zygmunt result. Well, now I'm trying to convince you that the study of those Calderon-Zygmunt operators for last 70 years, they eventually were reduced to the study of the estimates like this. So have a look, what is this? Again, how do we think about this? We think like this. Distribution function of TF is majorized, pointwise, by the distribution function of Cesaro plus dual to Cesaro applied to F. That's how we think about this. Coming to this interpretation, well, it took quite some time. And to me, at least with a person of my education and interest in mathematics, is mostly coming from the fundamental theorems of Boyd. I still think that in all interpolation theory of linear operators, those papers by Boyd and the introduction of so-called Boyd indices is still the most deep and important part of this interpolation theory in function spaces. So, what was Boyd concerned? He was asking the following question. I actually even took his PhD thesis, copies of his PhD thesis, to look how he wrote it. So he stated like this. So okay, we're looking at the Hilbert transform. We take two spaces, two function spaces, x and y. He's asking the questions, what are the conditions on these two spaces, x and y, such that Hilbert transform sends every element from x to element of space y. And he answered this question as follows, that as soon as we're working with LP spaces, P strictly between 1 and infinity, then we have this, this is satisfied. For LP, for example, for LP, this is satisfied. Well, okay, of course, this is the Riesz theorem, or actually immediate corollary of the Kolmogorov theorem, who proved his weak type on 1 result 15 years earlier than Riesz. But nevertheless, that's what Boyd, in fact, stated this question and proved, much more general result like this. And this is indeed a very useful approach to this. It's still, okay, I'm trying now to say that it took me quite some time to come to a little bit better viewpoint on all of this, completely stripping down all things about the spaces at which we work and so on and so forth, but concentrate only at the rearrangements. And the fact of the matter that one of the papers which was fundamental to further pursue this direction was when we were trying to do non-commutative kinship inequalities and the non-commutative analysis. That's sometimes very strange how things happen. All right, so still more motivation. Okay, so as I said, Hilbert transform, and it's studied, for example, by Boyd and many people after that. So there are a number of books here mentioned here. As I said, the talk was presented was written with the help of Fulin Yang, so he did not mention my favorite book on interpolation theory by Crane, Petunin, and Semyonov, which I still think is the best. But nevertheless, so this description how those behaves in Hilbert transform is now become a classical part of the interpolation theory. And have a look here. During this, as I said, I started to look at this at least around 2019. So we, in fact, were able to complement the estimate from above. We managed to complement and find also the estimate from below. So we obtained that, in fact, the Hilbert transform in this distributional sense is indeed equivalent to the sum, to the application of C plus C star, Cesaro and its inverse. That's the main ideology. It took quite some time before we sort of proved and showed that this is indeed optimal. It is optimal estimate. Quite a few years, but as soon as it is done, it was a natural question to ask what other classical problems in mathematical analysis and in operator theory could be profitably treated with our technique and with this new ideology which we propagate. So, for example, one of those interesting things which developed in this singular integral operator theory is commutator estimates. What are those commutator estimates? So the T here is still Calderon-Zygmunt or Hilbert transform. M phi is nothing but simply operator by multiplication on the function phi. So we're looking at the two operators, two classical operators, multiplication and say Hilbert transform, and we look at the commutator. In their fundamental paper, Koifman, Rochberg, and Weiss, Annals of Mathematics, 1976, they looked at the Ries transform. So T here would be Ries transform. So think about the Hilbert transform, and they proved that it is bounded if and only if the phi, this multiplication operator M phi, is given by the so-called BMO. So BMO, bounded mean oscillation spaces on RD. And well, okay, so you have a result, fundamental results for all P. So people would be, of course, expecting that that similarly to all classical results I cited, like Kolmogorov theorem, that it would be also weak L1 estimate. So that if you take phi from the BMO, then this operator will send L1 into the weak L1. That would be a natural expectation. Until in 1995, Perez, in the Journal of Functional Analysis, published a paper when he discovered that this is not the case, that this actually fails. So this operator fails to be with type 1,1, so not necessarily L1 sends into L1. And when phi is a BMO, and he published the following result. Again, when you look at this right-hand side, I think it will be a little bit difficult for people immediately, if you did not see the definition of and never worked with those spaces, it will be rather difficult. But this, what is written on the right, it is this so-called L log L space. This is the Orlich space L log L. And then what is stated here, that what Perez stated in his 1995 paper, that the distribution function, this is the distribution function of application of the commutator to F, is kind of majorized by the norm of phi, of F in this Orlich space. The funny thing is that, you know, I happened to start looking at this Perez paper about a couple of years ago. Back then, the paper in JFA gathered 200 citation, and well, okay, somebody told me very recently that there's already 240 citations. But the funny thing is that no one out of those 200 citations mentioned, and I looked through all of them, that the result of Perez was wrong. So this is also one of those funny things which sometimes, you know, happens so widely cited paper and major result is simply wrong. At least how it is stated and how it's proved. What is written here is already our interpretation of Perez's results. So we rectified his result, not simply like that. That this is, as I said, one of those remarkable things. So that's Perez provided. So I still think we don't claim anything. So it's his result, but as it is stated and proven, utterly wrong. 240 citations. No one says that. This is the correct statement. Here, I'm giving corrected statement of Perez's result. Statement was wrong, and since he was proving the wrong statement, the proof is wrong. This, sorry? Well, okay, those things were missing from the statement. Those multipliers were missing. He put them outside of the integral and proved But with the outside of the integral, the statement simply falls. You know, and when you read the proof, you realize it didn't work. But anyway, it's Peretz's result. So probably he meant like this. I don't know how things are. But the second is not. The second is not. You know, this is what I consider quite funny. And so we started to work. Firstly, I wanted to write simply, you know, the short paper saying Peretz is wrong. We will now rectify the statement. But fortunately, my younger collaborators are much deeper people than me, so they decided, no, we should really work and, you know, do things properly. And so our first result is the following, that, okay, let's have a look at this commutator estimate, and we give the distributional estimate like this. Have a look. It's so distribution function, when you apply the commutator to any f, is in fact majorized by the distribution function, when we apply to this distribution function of f, c squared plus c star squared. And that's, I think, is indeed a much deeper result than what is written in Peretz. But again, I'm very lucky that I have so many co-authors. And when I say this is much deeper result, and you can understand that I'm not simply talking about me. No, I'm talking about their contribution in the first place. Yeah? C is a fixed operator. T is a fixed operator, yes. Yeah, it depends. You take T arbitrary Calderon-Zygmunt. And this constant Ct depends only on this operator T. Yeah, you can vary T, and still it always works. And lo and behold, that in the special case when T is Hilbert transform, and we work in one-dimensional case, not in RD, then our estimates happens to be optimal. So I think that this is ultimate result about the behavior of those commutators M phi and T. Final results, sort of. I don't think it can be anyway improved in any way. This is our main theorem. And have a look here. You see, we encountered the situation when we now need to look at the powers of Cesaro operator and its adjoint. Now, yeah. Yeah. Then this. Here, you know, here, phi, no. Phi is here, you see, special phi. The second estimate is given for not arbitrary phi, but only for this log absolute value of x, whose norm is 1 and BIMSA. Yeah. So this is. And next theme, which we treated, so we started with this Peretz, you know, so it was. Okay, the next topic concerns the harmonic analysis about Marcinkiewicz multipliers. So what it is all about. So whenever we're dealing with this, any, say, smooth function, like from Schwartz space, when we split the real line into those dyadic blocks, k is integer, then we could consider Marcinkiewicz multipliers. That's how it is. So you take f, you take its Fourier transform, then you multiply by Fourier transform by this multiplier m, such that it has a bounded variation on every such dyadic interval. And then apply the inverse Fourier transform, and you obtain the operator Tm, which is called Marcinkiewicz multiplier. The study of Marcinkiewicz multipliers is a very well-known subject and theme. And of course, say this is a theorem of Marcinkiewicz, that if P is strictly between 1 and infinity, then every Marcinkiewicz multiplier is bounded in LP. But that people were interested not only, say, in the boundedness in the LP, but how constants in this, so you know, it is bounded operator on LP. What is the best estimate for its norm, you know, of this operator? And say, have a look here, and this is remarkable result of Bourgain. Bourgain, of course, has many remarkable results, but this is one of those who gave optimal behavior of the norm Tm when P is strictly greater than 2 and P goes to 1. It's, have a look here. Fulin, you certain that this both in the 3-2 or just one? Okay. So I read the proof, but now always confused how he could come with this very strange constant. So when P goes to 1, so P prime is the dual indicator to P. Yeah, P minus 1. So it is 1 over P minus 1. And have a look here. This is how the norm behaves. So before Bourgain, nobody, I think, could even guess that this will be like, it's very strange result. Again, this multiplier, again, it does not map L1 into the weak L1. That is, so again, this multiplier does not have weak type 1,1. And in a way, you could sort of guess here. So in order to have weak type 1,1, you need to have here not 3/2, but 1. I'm saying something on a very intuitive level. All right, so that's Bourgain's result, as I think fundamental. And if you read the proof, that it is a very much LP-oriented proof. So it was people were looking, and famous Terence Tao were looking at this question: what should be the replacement for weak type 1,1 result? And then he provided with a Tao Wright paper in 2001, he provided the following result that, you see, this is the distribution function of our Tm operator applied to F. And here you again see something what is nothing but the Orlich space norm, only not with log, but the log 1/2. And then what they proved, so they did it in 2001, and they worked, in fact, they worked on the space of finite measure. So their spaces L1 and L1 infinity was on the compact subsets of R. But very recently, Bakash, with his co-authors in 2024, managed, very complicated paper, very technically advanced, very difficult to read. They managed to extend it to locally compact case. So in fact, a result to those spaces L log 1/2. So you know, so you don't have from L1 to this weak L1, but you have actually this estimate like this. So, and our theorem is even more strange, but at very least I think you could see how does it come from. So where 3.3 divided by 2 coming from. So the result is the following. the behavior, this is, you remember, distribution function of TMF is majorized by the distribution function of what? We take operator C to the power 3/2. We take operator C star to the power 3/2. Don't ask me yet what does it mean 3/2. How do I define those positive powers, right? And then we obtain this estimate. And from this estimate, you will obtain the new proof of Bourgain's results immediately. Completely different method. As well as of those people like Terry Tao and Wright and Bakash and his collaborators. So, but you are, of course, should ask, so what are those? So how do you consider those operators, Cesaro operator, how do you raise them to the power 3/2? And again, this ideology coming from my rather recent investigations in the nature of, again, to the distributional estimates for Khinchin inequality in the non-commutative setting. And the definition of those powers of C alpha and C star alpha are given here. And to justify that this is, in fact, what is, it's a proper definition, I can say one thing, that this definition, in fact, provides the semi-groups of operators, and whenever alpha is 1, we recover the classical C and C star. Finally, we are coming to the next discussion, the next thing. It is very strongly related to Marcinkiewicz multiplier theorem, but it is the so-called Littlewood-Pelly square function, which is given as follows. So Lk, it is still our dyadic intervals. So we take function f. D here is simply our differentiation operator d on r. So it's a funny thing, of course, to write it like this. But again, I could not sometimes convince my younger collaborators and students that they should write a little bit more comprehensively. So differentiation operator, we consider its spectral family. Apply the spectral family and, you know, write it like this. But in fact, what is written here, it is the same as you take those dyadic intervals and take their square functions and look at this. So what is, again, Bourgain's result for the square function? Yeah. Yeah, they cover the whole R. Yeah, no, not essential. Not essential. It's plenty of those variations how you can cover the, but some conditions must be satisfied. So what is this result of Bourgain? Have a look. The square function estimate when p goes to 1 grows, its norm grows like this. This is p prime, what we say a dual indicator to p, to the 3/2 again. But when p is greater than 2, it is like p. Again, probably only, I think only the genius of Bourgain was able to do something like this and see such the results like this. So there was very, to my mind, again, one of those very beautiful results in harmonic analysis, and how we recast and reproved it. That's our last main theorem, which sounds like this. Whenever we look at this square function estimate and we look at the distribution of this square function S of f, then it is majorized by what? By the Cesaro to the power 3/2 plus dual to Cesaro without any power at all. So in a way, intuitively, you probably would see that this, you know, this Cesaro into the 3/2 responsible for that estimate, and Cesaro star is responsible for the second part of the estimate. But this is, again, of course, from this result, you recover everything what all previous results, those Bourgain results like this, and you see that we are able to obtain all of those distributional estimates in the terms of this new operator semi-groups associated with Cesaro and the Cesaro star operator. I'll finish this talk with the one application to my topic from which I many years ago started to look into mathematics and these questions. This is again interpolation theory, and recall that the quasi-Banach or Banach, whatever you can do whatever you want. Quasi-Banach space E is called an interpolation between LP and LQ. Let P and Q between 1 and infinity, such that it sits in the intersection of two spaces and sits inside of the sum of two spaces. And if every linear operator which acts on the sum, such that it sends LP into LP and LQ into LQ, necessarily sends E into E. So that's the meaning of interpolation theory. And the interpolation theory works with trying to describe the class of interpolation spaces in various pairs of Banach or quasi-Banach spaces. And okay, so we can write the following corollary, which was previously unavailable. Why? So let me state the corollary, and then I explain why it was not available before. So let E be a symmetric quasi-Banach space, which is an interpolation between LP and LQ. Let T be Calderon-Zygmund operator, Tm be the Marcinkiewicz multiplier, and S is the Littlewood-Paley square function. And then we can say that operator M phi comma T with phi in BMO, Tm and S are all bounded in E. In other words, in this corollary, we not only recovered but all those classical results due to Bourgain and many others, but we managed to immediately extend it to the large class of interpolation spaces. Why this become possible? Well, because all original results were not suitable for interpolation. There was not a single operator which would be acting on those spaces to which behavior we could attribute this or that inequality. So it was, every time it was a little bit ad hoc. But all our theorems which I stated today at this talk, they are already show to you that all we can reduce to the action of the very concrete operators. C to the power alpha plus C star to the power beta for various alpha and beta. And as soon as you have, say, this distributional estimates for this one single operator, C to the power alpha plus C star to the power beta, then interpolation becomes immediate. It's becoming straightforward application. And from this point of view, I think, say, the value of our results are quite clear and allows to give I think, much more rounded point of view on the nature of these three classical results by Peretz, by Bourgain, and by Territau. This is probably a good place to stop. Thank you for your attention.
Thanks, Professor Sukochev's beautiful talk. Any question?
The function mu you introduced, it is inverse to distribution function.
Yes.
But you keep calling it distribution function. Yeah, I'm not arguing about that. I'm asking, is it more convenient to represent result for inverse distribution rather than distribution function? There is a connection between.
I was brought up what this function mu in the classical analysis is denoted by the f star. So whenever you look at any function, then you can rearrange it. Say, suppose your measure space consists of n points. Then your function is simply a vector, n-dimensional vector. Then you can arrange it in the decreasing order. And that's what was called A star. So you have a vector A with a positive components. A star is the decreasing order. When you go into the, say, non-atomic measure space, then you have to do a little bit more work. But this is what Hardy and Littlewood did. With every measurable function on 0, 1, you can positive, okay, at the moment, positive. You can associate the function f star, which has exactly the same distribution, which is right continuous and decreasing. I like, because sort of I was brought up this way, to look exactly at this function f star, which here into the note to my own book, I write mu. But no, a lot of people write mu. It's not necessarily me. And it is traditional to write it in this way. However, if you look in the nature of the things, then you can rewrite all of those results using only the distribution function. That's it.
Any other question?
I want to ask, are these questions can be reformulated in no-commutative LP spaces or quantum symmetries?
This is a question which bothers me already for quite some time, and which I was going to hire Fulin Yang to work on this. So it was exactly what I really would like to do. So you have a classical harmonic analysis questions like, say, for LP of R. Now or for, say, LP of T, torus, LP of TD. So you look at the torus, okay, suppose. That's a classical harmonic analysis. You look at this, say, square function thing, and or for those multipliers, Marcinkiewicz multipliers, and then you have those beautiful Bourgain's results. Okay, so now let us move on to non-commutative torus or to non-commutative Euclidean plane. Okay, I don't have any more Fourier analysis for Euclidean plane, but I do have still a very nice basis, Schauder basis, in the LP of TD theta, the most studied object in non-commutative geometry and non-commutative analysis. What are the analogy of those results? That's a very nice and very deep and serious question. And as I said, I was hoping that Fulin is the person who is able to attack this question and make some progress on that with the help of my group in Sydney. But as I said, well, I'm here to tell him work harder.
Thank you.
It is very interesting direction. I don't see how yet it can be done, but it is a very serious direction.
Thank you very much.
Any other question? Okay, if there's no question, let's thank the speaker again.
Thank you.